welcome to the first stream in our live tours Q&A series for the Pint of Science Festival. My name's Jirana and I'll be your MC today as we look into the labs of Aussie scientists and learn how they work on a daily basis. We've asked our scientists to pre-record their lab so we can stop, rewind and replay sections without disrupting the research. Now, throughout the live stream, you can join in on the conversations in the comment sections to the right of your screen, or over to Twitter you can head to, and make sure that if you are going to use Twitter, make sure you include the hashtag PintAU21, which is also up on the screen right now in the corner. Now, we'll leave all the bigger questions to the end of the tour, but if you do want us to stop the video and chat about something cool, let us know. There is a little bit of a delay before it gets to me as a host, but we'll try to stop as soon as we can and showcase what your question is. Now, you might notice me dart my eyes off in different directions. That's just me talking to my lovely crew here today. We've got some amazing people helping me tonight. We've got Karen and Steph who will be helping me with moderating the questions and sending the questions through to me. And I've also got Tom who's going to be working the camera magic. So if you see me yelling at Tom, that's probably what I'm up to. But there won't be any yelling today. Now, when we hold events at pubs around Australia, we ensure that we recognise the local Aboriginal and Torres Strait Islander nation, one of many that makes up the continent that we now call Australia. Now that we're holding this event online and our speakers and much of our audience is streaming from around Australia or even the world, we want to acknowledge all traditional custodians of the country, the first innovators and scientists of this land. We pay our respects to Aboriginal and Torres Strait Islanders, elders past, present and emerging, and recognise their continuing relationship with the land, waters and culture. Especially we would like to pay our respects to the Kulin Nation, who are the traditional owners of the land that our tour location, the Australian Synchrotron, is built upon. Now, I'd like to now introduce you to our tour guide for tonight, Dr Eleanor Campbell, who is a PhD in biochemistry and currently works as a beamline scientist at ANSTO. Dr Campbell, thank you for joining us today and showing us your lab. To start off with, could you tell us a little bit about yourself?
So I am a beamline scientist here at ANSTO. I've been working here for about 18 months, and hopefully by the end of this tour, the phrase beamline scientist will actually mean something to the audience. You'll learn what a beamline actually is and why we need specific scientists to work on them. But a bit about me, my background's in biochemistry. I studied biological molecules like proteins during my research career, and now my job is to facilitate other researchers coming to the synchrotron and making use of the amazing equipment that we have here.
That is really, really awesome. And I'm really looking forward to sharing this experience with you. I've never actually been able to find the time or be in the right place at the right time to see inside the synchrotron. And I think for a lot of other people as well, we're really looking forward to seeing all the cool things you're able to show us today. Now, Tom, I was wondering if we could, or maybe you might not have this on hand, I was wondering if there's a map that we could have a look at. Now, yeah, I thought he might give that look. So while he has a little bit of a panic as to whether or not there's a map about that we could have a look at, Eleanor, how often do you spend your time at the synchrotron?
Look, pretty much all day, every day. These days, being down here on the beamline, so I'm actually, this isn't a virtual background, I'm sitting on one of our beamlines that you'll see in the footage coming up. Back when I was a researcher using the beamline, I was accessing it remotely, so usually at 3 a.m. from an office in Canberra at ANU. So a very different experience with the synchrotron, and it was definitely a big experience coming on site for the first time and seeing the scale of the place. And I hope that the videos today kind of show the audience the scale of the place, because it's huge. We produce light 1 million times brighter than the sun in a facility that's apparently about the size of the MCG. I'm not a sports person, so I don't know how big the MCG is. In my mind, the MCG is about the size of the synchrotron. So, but yeah, I really hope that the scale of the place comes across and the sheer volume of research that happens is carried across.
Oh, okay. So we've got a good map now looking here. Oh, it really does look like the MCG in honesty.
Maybe a little bit more crowded.
Yeah, I'm sure we're going to get comments of people telling us that it looks nothing like an MCG. Now, just having a quick look at this, on the map, where is the entry point?
Yeah, so down at the sort of, if you look at 6 o'clock on that donut shaped, our science donut, that's the main entrance that we'll be heading into. So just to kind of give the audience a little bit of an overview of what a synchrotron actually is, so that the footage makes a little bit more sense in context. What we basically have here is a giant particle accelerator that is shooting electrons at nearly the speed of light around these big rings. So you can see that at sort of position 1 and 2, that's labeled LINAC, or linear accelerator. So we'll see a little bit of that in the tour. Then that feeds into the booster ring, which is one donut, and then that kicks out into the storage ring, which is the next donut out. And then these branching sort of blocks coming off that storage ring tangentially to that ring, those are the actual beam lines. And I guess an analogy for what this sort of system is I like to think of it as a bit like a Swiss Army knife, right? So it's one facility, it's one tool, but each of these beam lines has a different purpose and acts as a different instrument or a different tool to fulfill a different scientific purpose. So there's overlap between some of them, and some of them have very, very specific jobs. And we can go around and I'll point out the different beam lines. So lines shooting a beam coming off tangentially from that ring. So if people do have questions about how they work and what kind of research is done on each one and what makes them different from each other, I'm super keen to answer those sorts of questions too. So that gives you kind of a bird's eye view, and then hopefully the floor will make more sense as you walk through now.
Oh, excellent. Well, now I understand why people call it a science donut. It really is a series of donuts with Swiss Army knives.
Yep.
So now that we have a bit more of an idea of the overall arching, how the map looks, let's have a look at the video now. So let's have a look at this first one, and I think we're at the entrance.
Yeah, so I think the footage starts off with the entrance of the building. So it's kind of a little bit like play school. We've got our square building and our round building. So that over in the back there was the square building. That's where our managers and executives work. We have an auditorium and office space there, and we're just walking towards the round building now. So this is where the actual science is happening.
So could a general member of the public get into the building?
Not without having been signed in and having a visitor pass. So for a lot of the conference events we have, they can access the rectangle building, the square building, but to get into the round building, you need to be wearing closed-in shoes. You need to have been escorted by a member of staff to take you through. And so just in this footage here, we're heading up the stairs. There's sort of two sections of the round building. There's the tech floor, which is sort of ground level. And what we're doing now is just heading up onto the mezzanine. So this is a ring of walkways around the top of the synchrotron. And this will kind of give you an overview of the whole facility. So yeah, hopefully you can see how big it is.
Wow. So hang on. Yeah. What are those coloured bits of blocks off to my left? I'm not sure if it's your left or right.
The sort of
like the yellow and the orange. Yeah.
Yeah. So those are actually computer racks. So there's obviously a massive amount of computing power that is necessary to keep all of these systems running. So the big colourful sort of cabinets are full of different computers and control boxes. And I believe, so that's the medical imaging beamline, and the principal scientist of the medical imaging beamline insisted that he have one rack in each colour, including a brown one that he decided he didn't like the look of. So our beamline stole the brown one. So that's
okay. So we'll look out for the brown one then.
Yeah.
Alrighty, let's keep going. Let's see what else we can find and see. Ooh.
Yeah, so that's sort of a massive roller door at the other end. Oh, there's Bruce. He interrupted my tour to say he wanted to be in it. So a massive roller door at the other end for craning in equipment. So that opens all the way up to the ceiling, which is about as big as you need to get all the components for the actual storage ring into the facility. And then you can see some of the storage racks. Obviously, a lot of equipment that we can sort of look through in a little bit more detail as we wander around the tech floor. But this one that we're above now is an interesting beamline. So this is the medical imaging beamline, and it's an interesting one because it actually extends about 120 meters outside of the building. So rather than being contained within the donut, it actually offshoots to a separate building. And that beamline is currently in development for use in clinical purposes. So actually having patients come on site and have CT scans. So the same way that you'd have a CT in hospital, if you're, say, having a scan to identify a tumour, the medical imaging beamline are currently building that capacity into their beamline as well. And they can do that because it's that clinical section is so far away from the storage ring. If you imagine holding a torch really close to a piece of paper, you've got a very tight, hot little beam of light. And if you pull it, all the way out, then you've got a much more diffuse, sort of spread out, less intense light. And so that light is then safe for people to be imaged with in obviously a very controlled and monitored way. So there's some really cool work happening there.
Yeah, right. So does that mean in the other beamlines, you can't get anywhere near what you're doing, or?
Yeah, and what you'll see in some of the footage coming up is the amount of radiation shielding that has to be present in order to keep people safe. So this is ionizing radiation. The light that is being produced by the synchrotron radiation, is very, very high energy. So on the beamline I work on, it's X-ray energy. So obviously when you go and have an X-ray done in a medical sort of context, you're very carefully monitored. The radiographer will typically set you up and then duck behind a little shield and take the images and then come back and reposition you. And that's because they don't want to be overly exposed to X-rays. And the same thing counts for us here. So anytime that the synchrotron is on and producing radiation, we're making sure that humans cannot be anywhere near any of that high energy ionizing radiation. Yeah.
How very interesting. Now, I did ask Tom to pause the video for us because I noticed something, and I was just going to ask, what is this?
What is what?
So I can see there's a lovely rainbow flag,
Yes.
and it's what is the instrument that it's attached to?
Okay, so the rainbow flag is because we have recently had a couple of different Pride events. So we have the ANSTO Ally Network, which is a really important part of our diversity and inclusion programs here at ANSTO. So I think we had a morning tea with cupcakes and sprinkles and everyone wearing rainbow colours and taking photos in front of the rainbow wall, which was very nice. What it's attached to is actually a section of the synchrotron. So it's not an active section, it's a section that's been pulled out to serve an illustrative purpose. People can actually go up and stick their hands in it and have a look at how all the magnets fit together. And we'll get a closer view of some of that stuff actually inside the tunnels when we wander in there on the tour.
So much to go. We better keep on going. Hey.
That's the tea room.
Okay, very important room.
A tea room, yeah.
I hope that tea room doesn't serve just for you folks, just for everyone.
So as we're just walking past this one here, you can see this is X-ray fluorescence microscopy. Basically every beamline has a 3-letter acronym. So please forgive me if I'm talking in 3-letter codes, but XFM do microscopy where they can actually map where in an object different atoms are. So they actually got a little millipede off the tech floor once. It had long since died. It was a dead bug. And they put it in their imaging to identify where in the body of the millipede zinc and copper were accumulating. And they can actually paint those different colors computationally, and you can then sort of have this beautiful 3-dimensional map of where the different chemical elements are in different test subjects, like sad dead millipedes. We're just walking past the control room here, so this is a really important part of the facility. This is where the operators work, and it's basically like the NASA sort of hub. They've got countless computer monitors that are constantly monitoring how the particle accelerator is working, how each of the beamlines is working, and they are also first aiders and fire wardens. So if anything goes wrong in the facility, we run up to the operators and we beg them for their assistance. They're great.
Oh, sounds like they are very, very important people.
Yeah. So this is the tech floor now. We're down on ground level. This is MX that we're walking past. This is the beamline that I work on. You'll get a bit more of a view in there in a little bit. That's just our screensaver playing Pong with itself.
What's happening on that screen there? Is that everyday normal occurrence or?
Yes, this is us mining Bitcoin. No, this is we have an assortment of fun screensavers. We like to, we have to make our own fun sometimes in science, Jirana.
No, that's a fair call. So this is just a background. This is not everyday work.
Yeah.
Okay, just checking.
But it does capture people's attention when they walk past.
It captured our attention.
Yeah, exactly. We have a 4K screen just next to it that we use for video conferencing with researchers. And we've taken to putting up like 4K aquarium footage and things just to sort of calm people down in the facility.
That sounds like it'd be really fun to watch.
Oh, yeah. One of the other things that you'll notice a lot as we're walking around is there's a lot of construction work going on. So at the moment we have 10 different beamlines, so 10 different instruments branching off the central storage ring. But we're in the process of building 8 more. So a lot of the floor space is going to disappear. And you'll see different sort of new beamlines in various stages of construction as we walk around the tech floor. What are we walking past here? This is IR, so we're walking past infrared microscopy. So this is actually using very, very low energy light, so infrared, so less energy than your standard visible red light. And they can use this to study all kinds of different things, including gases that might be present in outer space. They can learn about, the different absorption qualities of those sorts of atmospheric gases, and they also do all kinds of cool stuff with looking at dating paints and things like that. So they can be involved in a lot of curation and historical and anthropological work too. We like to say that any topic that you're interested in, there'll be a beamline somewhere at the synchrotron that will have something for you. So try me, if there's some topic you're interested in, throw it in the chat and I'll see if I can link it back to one of the beamlines.
So we actually do have a question from Richard. He says, can the XFM beam be used to detect lithium positions?
Lithium. I think lithium it might be a little bit small for XFM. I can definitely give Richard the contact details of our XFM scientists. He's super keen on finding lithium in things. But yeah, XFM, I know that they can do anything sort of in the metals, so that first batch of metals, but whether they can do something as small as lithium, I'm not 100% on.
Well, it sounds like we'll get back to Richard on that one.
Yeah.
I have one more question that's come through, and that is, would you call the synchrotron itself the tunnel? What is the definition of synchrotron technically?
Yeah, so the synchrotron, technically that only refers to one of the donuts. So the middle donut, the very inner donut, the booster ring. So synchrotron actually gets its name from the fact that we're accelerating little packets of electrons at nearly the speed of light. And all those packets have to be perfectly synchronized with each other as they do these high-speed laps around the donut. So that is the actual synchrotron bit, and those electrons whizzing around inside that tunnel, which you'll see the tube itself soon. That's the synchrotron bit. Everything else is either giving energy to those electrons or then taking energy out, which is what the beamlines are doing. So if we're kind of looking at it at a really fundamental level, the electrons are whizzing around the donut, and every time they have to bend, they lose energy. So the momentum of those very, very fast electrons is being lost slightly as they move around a corner. And as they go around a corner, they lose that energy in the form of light. And so that's that tangential beam of light that comes out. And that's what's being fed down the beamlines. So yeah, the synchrotron is sort of a catch-all term for the whole facility, but really technically just refers to that storage ring that you'll see in a little bit, the booster ring that you'll see in a little bit.
Yeah, right. So if I was talking to someone, I could say the donutty thing, and they'd be like, yeah, the synchrotron. Yeah, that's the same word we have for it.
Exactly.
Okay. Well, that sounds really, really lovely. Now, I saw a little snippet of the next video that we're going to head off onto. And I'm just trying to actually stall for Tom, who had to go deal with a very loud cleaner.
Oh dear.
But we're now in a position to, let's have a look at the next video and see what's going on.
Cool.
So where are we now?
All right, so we're actually climbing up onto the roof of that storage ring. So this is where our high energy electrons are being kept and then fed into the beam lines, or sort of whizzed past so that the light can head into the beam lines. You can see there's a massive amount of cabling and pipe work. The facility here is run by like the combined effort of a cast of many, many people. I think there's 170 something people who work here, and that's scientists, yes, but also electricians, mechanical technicians, robot controls engineers, obviously an amazing cleaning staff who have been working really hard in the past sort of 18 months or so, people who are experts in scientific computing and IT. It's honestly an astonishing combination of very, very talented, clever, hardworking people who can make this massive machine actually operate, and really reliably too. I think that when we look at the statistics for like how often the machine stops working, my dishwasher stops working more frequently than the synchrotron does, which, given the different scales in what they're achieving, is pretty cool.
Now, I've just asked Tom to stop because I wanted to see, what are these orange square things we're walking past?
Yeah, the really massive ones. So
Yeah.
those are basically huge power banks, massive, massive high voltage sources of electricity. So obviously, to get electrons to close to the speed of light, you've got to feed them a lot of energy, because as they approach that, insurpassable speed barrier, as we get to the speed of light, they are, well, we can start talking about Einstein. They're sort of getting heavier and heavier and heavier because of relativity, right? So this is why we also have amazing particle physicists who work here as well, because there's a lot of relativistic things that have to be thought about as well. But these are the power banks that actually put that energy into the electrons in the form of radio waves. So the same sort of long energy wavelengths that carry radio signals. They're pushing that energy into the linear accelerator, which is a tube that you're going to see in a little bit. And hopefully that will sort of put it into a bit more context.
Yeah, right.
So
okay.
You don't want to stick
going.
a fork into the back of one of those.
Oh, gosh. Yeah. No, we shouldn't even do that into a toaster. So.
No, definitely.
So, as we're going through, what would be a reason someone would need to hop onto the roof into this area?
Yeah, so a really good question, and basically maintenance and sightseeing, I guess. Anytime, at the moment, we've got a lot of contractors in who are working on building these new beam lines, and obviously all this infrastructure of electricity, plumbing, that's the other thing, all of these components have to be cooled, and they're cooled by water, so that plumbing has to be built in addition to the electrical cabling, in addition to all the computer controls and all the safety controls. Everything in the actual tube, where the electrons are whizzing around, is under extremely high vacuum. There's a lot of vacuum. So 10 to the power of -10 atmospheres. So that has to be maintained by amazing vacuum technicians as well, and that's why they'd be up on the roof.
Okay.
We're walking into the linear accelerator now, I think. I do get lost. Yes, okay, here's the linear accelerator. This is like the star of the show. So this is where it all kind of starts. We have an electron gun at this end that we're just walking up to now. And this is where our electrons are generated and then shot out. So about a meter down this tube, those electrons are traveling at 99% of the speed of light. By the time they're at the end of this linear accelerator section, which is about 12 meters long, then they're traveling at 99.9987% of the speed of light. So they go very fast, very quickly. I guess that's why it's called an accelerator. It's really doing the hard yards to accelerate. So this is lots and lots of copper rings that all vibrate at a frequency that allows for the electrons to basically surf that wave of energy that was coming out of those big orange boxes. And those electrons surf along. And now I don't know if this is true, which is bad science communication, but I was told when I started working here that each of these copper rings was hand tuned by a German man who sits there and like listens to them and taps on them. But that does actually, now that I say it out loud, sound like something that was made up.
I've heard this story before.
You've heard it too? Awesome.
I've also heard this as a myth, but hey, maybe we should ask Mythbusters and get them involved. Yeah. But that is really, really cool and probably a really high-paying job.
Yeah. So we keep that copper at 40 degrees Celsius. So you just saw me sort of touch it gently there. When we have tour groups come through, you can touch the linear accelerator. Obviously, this, I should stress, none of this is on at the moment. I'm only allowed in the tunnels because the machine is not operating. If the machine was operating, we would not be allowed anywhere near the tunnels.
That would explain all the big signs we saw on the way in.
Yes. Stay away. And then this is the synchrotron itself. So this is the booster ring. So that sort of inner donut where we're first kind of speeding up those packets of electrons. Well, they're already sped up, but we're circulating those packets of electrons so that they're all synchronized with each other. And we can keep adding more and more high energy electrons as required. And then those will get kicked out into the storage ring where we can then take that energy in the form of light to feed our hungry beamlines. But yeah, this tube is actually, that's what's evacuated from air. So that's the vacuum bit. And the electrons are whizzing down that tube. And the big sort of square things that you might have seen back there are actually magnets. So the electrons are kept in the middle of that tube through a series of very powerful electromagnets that are basically shaping the beam in the horizontal and vertical. And then there are big magnets that you'll see later on that bend the electrons around the corners of the synchrotron. So rather than a donut, it's probably actually more like a 50-cent piece. So it's lots and lots of series of straight bits with little bends in them.
So is this the other side of the beamline that we're seeing now? Or just Sorry, can we go back a little bit, Tom? Yeah, this. Is this the other side of it, or what is this bit?
That's the other end of the donut. So we looked out one side and now we're looking out the other side. So this is still the booster ring. And then to actually get into the storage ring, we have to go up over across the corridor and into the next section of tunnels, which we'll do in a second. So yeah, this is, I think it's about 160 meters around. So, if you wanted to do a few laps of it, you could get your steps in. Have better places to walk than in a very expensive, highly technical piece of scientific equipment. But, if you really wanted to.
Well, actually talking about steps and stuff, someone has actually asked, how long does it take to start the synchrotron? And is it a huge job involving lots of people, or is it just like a little switch?
If we lose beam, which does happen, so you'll often, you'll hear scientists being upset, the beam dropped, I lost beam. And that's typically if something has gone wrong, and it doesn't even have to be something actually going wrong. It can be any one of the many, many, many safety systems being tripped. So if at any point the machine feels like it is going to be put into an unsafe state, it will switch off. And we can get beam back in about 20 minutes. And that's the operators upstairs, that control room that we saw earlier. And they are basically trained to restart the machine to validate, what went wrong, how do we restart it safely. We can bring back the experimental facility in about 20 minutes. Now, at the moment, we're in a shutdown period, which is why I could take you through the tunnels. And that lasts for 4 to 6 weeks, depending on what time of year it is. And that's when a lot of the maintenance is done on the equipment. So researchers are not coming in and using the synchrotron at this period of time. Actually getting the machine up and running at the end of a shutdown is a bit more of a job, because usually lots and lots of work has been done that then needs to be checked, double checked. Systems need to be restarted from scratch. So that can be upward of quite a few days to get it back into a healthy state.
Holy
But that's all
moly.
scheduled into maintenance time. Yeah.
How much does this all cost? Or like, how much does it cost to run the synchrotron?
So that's a really good question. And I've been told that in terms of the electricity consumption, we are on par with Chadstone. So if you've been to the Chadstone shopping mall, we're basically like running a standard big shopping mall, which is a good way to kind of balance it up in your head. You know, do you want to go to Cotton On, or do you want to investigate the secrets of the universe? I mean, sometimes both, right? But yeah, that's kind of what our running costs in terms of electricity consumption are equated to. In terms of other things, one of the more expensive resources that we go through is actually helium. So helium is something that there is a big kind of protection around, because we're going to run out of helium eventually. And the analogy that I've heard is that where liquid nitrogen, which is a solution that a liquid we use a lot on MX, that costs about the same per litre as milk, whereas helium costs about the same per litre as very, very nice whiskey. So that's when you'll go through many, many, many hundreds of litres of liquid helium to cool the medical imaging beamline. So I don't know, do the maths on how many bottles of whiskey it would cost to run the synchrotron.
Oh gosh, whiskey. Whiskey is a very, very expensive thing.
It
So,
can be, yeah.
when it is running, is it running 24/7? Or is there like a certain period of time that it's working through?
Yeah, so during our user runs, so when we do have researchers coming on site and using the equipment, the synchrotron will be active 6 days a week. So it runs from Tuesday through to Sunday. And then Monday, we usually have set aside for weekly maintenance. So running in, checking everything's still working. In the case of MX here where I'm sitting, we have to vacuum the beamline literally with a Hoover just to like tidy it up. Do all our sort of admin tasks and get things ready for another week of experiments. But it is running 24/7, and we do have staff here 24/7. Those operators are constantly around, security's around, and they're sort of first point of contact for any scientific questions or any problems that are happening. And if there's something that is outside of the scope of what they can do at the time, then scientists get called back in. So we do have an on-call roster, like doctors in medical dramas, where we're not supposed to be out drinking that whiskey, because we might get a call saying you got to come back in and fix the beamline.
Yeah, right. Have you been called, while you've been on call, have you ever been called in?
No, I haven't actually. We took a break from doing the on-call stuff because of mitigating circumstances. We didn't want staff on site unless it was absolutely necessary for a lot of last year. MX was operating a lot of last year because we had a lot of researchers who wanted to make use of the beamlines to look into different COVID-19 proteins. But we haven't actually been doing on-call since I've been working here. So, we'll see if we keep this, or if I'm going to have to get into the habit of having my phone on loud after dark.
Well, hopefully I haven't jinxed it for you. On that note, let's head back to the videos and see the next little bit we've got on.
Cool.
Alrighty, so having a last look at the beamline, and then where have we
Right,
ended
so
up now?
We've jumped across into the storage ring. So this is the outer donut. This is actually the superconducting wiggler. That's its technical term, actually. And that's what's powering that medical imaging beamline that's going to do clinical stuff eventually. It's doing a lot of really cool research stuff at the moment, which I'm happy to talk about. But now we're sort of walking around this outer donut, the storage ring. Lots and lots of big electromagnets to direct the beam. You've got that tube where the electrons are whizzing through. I basically want to walk around to this big pink box here. So this is an undulator. This is, we will turn around and look at it again. I think I was trying to see if I could see my own beamline out this hole. Yeah, there we go. That's MX. Normally that is closed. So once again, maintenance. So a lot of the doors are open. Those are massive cement doors that require a proper mechanical tug cart to open them. They get lifted up on air bearings. so that there's no friction, and then they get pulled aside by a machine because they're so heavy you can't just pull them open. The big pink thing that we saw is one of the
can we
pieces
go back
of
and have a look
equipment.
for it? Hang on.
I think it'll pop up.
Pink
It's
thing.
hard to
Pink.
miss the big pink thing.
This thing?
No, I think it's a bit. I can't tell that. Yeah, that boy. Yeah, him. So that is an undulator. That is actually taking the electrons that are whizzing around the storage ring, and it's making them sort of bounce left and right, left and right, left and right, or up and down. I'm not entirely sure. But it's basically sending them on this little sort of wiggly path. And every time they go on a little bounce back and forth, they're releasing that energy in the form of the X-rays. And this is the source of the ultra bright X-rays that we use on MX to look at the three-dimensional structure of protein molecules and other chemical molecules. So when we look in the hutch, you'll see a bit more about how those X-rays are actually being used, but that's where they're coming from, basically. So I like going and looking at the undulator because it's sort of like, I don't know, the grandparent of my X-rays. Sorry.
That's all right. I think everyone's got their own analogies for things, and I think surely grandfather or grandparents are probably nice and relatable. So what are we? Oh no, we were looking at this before, weren't we?
Yeah. So this is all the massive magnets, and
so
like I said, we're building. Yeah.
Does the magnets, these big massive magnets, they go around the whole outside, the whole
Yeah,
donut?
yeah. So they are sort of on every little stretch of the. Well, there's another pink thing. Every little stretch of the tube that the electrons are traveling through to keep them focused, basically. So those magnets, because electrons are charged, they will react to a magnetic field. So by having these big electromagnets wrapping around the tubing that the electrons are going down, we can keep the beam nice and tight. We don't want it sort of splaying off and hitting the inside of that tube. We want to keep it all nice and sort of like threading a needle straight down the middle. And the magnets are what do that. They keep it the right shape and size.
I would hate to try to find out if there's something wrong with one of those. Like, is there a way to try to figure out, like, you know, it's wrong with this one's got a mistake going on with it? Or how does someone who's needing to fix this know which one they're going to need to go fix?
Yeah, that's an awesome question, and it's an intimidating thing to kind of get your head around. Last week I did have a little bit of an existential crisis about like just the amount of stuff here and the amount of things that can go wrong. Nothing can go wrong in an unsafe way. Everything is built to fail safe. But in terms of actually figuring out what is wrong, first of all, we have people who are insanely highly trained in understanding accelerators and understanding beamlines and optics and the different components. There's also a lot of diagnostic tools inside the synchrotron. So where the beam, we have a thing called a beam positioning monitor that will actually be able to display to the accelerator physicist where the beam is sitting inside a little window that they're monitoring. At the moment, the beam is incredibly steady when the machine is on, but once upon a time, it was much more sensitive to vibrations in Earth. And apparently the Christchurch earthquakes actually were picked up on the beam position monitor at the Australian Synchrotron. So they could actually see in the trace of where the center of the beam is when that earthquake finally sort of propagated through and reached Melbourne. Which is, you know, not a technique that you would have thought the synchrotron would be involved in, but there you go. It can do anything.
Wow, it sounds like the world's most expensive seismograph.
Yeah, it's the world's most expensive everything. No,
yeah. Alrighty, let's continue on and see what else we can find.
All right, so we're walking past. This is soft X-ray.
Soft X-ray? What does that mean?
X-ray. So these are slightly less energetic X-rays than the ones that we use on MX. So one of the reasons that you can actually see this really sort of attractive beamline with lots of different bits and foil is because X-rays are much lower energy. They don't need to be kept in a big mint radiation shield. They are kind of free to, they can be stopped by just foil and aluminium and stuff. So that's why that beamline was used as the backdrop for a Nicolas Cage film called Knowing. So if you're ever watching that film, you will see soft X-ray and a couple of the soft X-ray scientists in the background holding clipboards. So we do get used as a location for films that have to look very sciencey.
So hang on, we just went past something that I'm not very sure what it was. It was like green, and it looked like windows and doors.
Green and windows and doors.
Yeah, sorry, maybe there wasn't windows. Keep going back, Tom. Keep going back. That thing.
Oh, yeah, okay. So, yeah, this kind of gives you an idea of the variety of things you'll see inside a beamline. So back a bit earlier, we saw soft X-ray, which was all that sort of very sciencey looking equipment. Yeah, head on back, Tom. That was not shielded. This beamline is, okay, so yeah, here's soft X-ray. So all of their equipment is out in the open. You can actually look through those viewing windows and see the beam. You can see the X-rays as they interact with materials that are being tested. Soft X-ray is used.
Are you saying I could see the beam, like physically see a beam?
You could physically see a beam on this beamline because they get to low enough energies that there is a bit of a glow of visible light as well.
What color? Just out of curiosity.
It's probably, well, so if we're thinking about the spectrum of colors and their energies, it'll be at the higher end of that. So the higher energy colors are purple and blue. And then those lower energies are down in kind of the red and yellow. So you'd be able to see maybe a little bit of a blue or purple tinge, just sort of emitting from their equipment there, inside the equipment, not outside. They use this equipment to study surfaces. So they look at the chemistry at surfaces. So they look at a lot of things like batteries, batteries charging and discharging, different materials that are being designed, ceramics and things. So they do a lot of really awesome stuff with technology and those sorts of applications. And then if you go to the next beam, so this is a beamline, and we're going to the next beamline, which is SAXWAX. I told you there's a lot of acronyms, so that stands for Small Angle X-ray Scattering and Wide Angle X-ray Scattering, SAXWAX. And their setup is all inside this vacuum hutch. So they're actually doing experiments at the moment, not only inside a radiation shield, but then once again inside another protective layer so that their experimental conditions can be monitored really carefully inside this. So every beamline, like I said with the Swiss Army knife analogy, you've got a corkscrew and you've got a Phillips head screwdriver. They're very different tools, but they're all part of the same kind of overarching structure, and they have very different jobs.
So what is the main job at that facility, at the SAXWAX?
At SAXWAX, so they look at scattering. I know that you can use scattering to look at the sort of broad three-dimensional shape of biological molecules. So that's an area that I'm slightly more interested in. So you can actually see whether, for example, a protein is a big round sort of squishy ball or a longer squishy tube, based on how it's moving and how light that X-ray is scattering off the samples there. So they'll have a lot of stuff that they're doing with basically biology and medicine. There's a new SAX beamline being built right next door to us, BioSAX. So that's going to be the next one that construction will start on, which will mean that our beam will be vibrating a lot when they're drilling into the floor. But that's okay. We will persevere. And they'll do a lot of stuff looking at different biological systems in solution. So how biological molecules behave in water rather than in crystals, which is what I typically look at. Yeah.
Gosh, there is so much that happens in this one big place.
It's a busy, busy place.
Yeah.
So this is a chemistry lab. When users come on site to perform their experiments, they might be bringing in different chemical reactions that they want to carry out. This is one of the facilities that they have access to do those chemical reactions and then quickly analyze the results on one of the beamlines, or they might be setting up an experiment in here that they then take into a beamline and put in front of the X-ray or the infrared light, whatever their requirements are. So that's just a quick wander through the chemistry lab. Actually, I was multitasking there because I was doing a safety inspection of that lab, and I was like, I can do both at once. It all looked good. This is a hutch in the process of being built. So this is all the radiation shielding going in for one of those new beamlines.
Oh, cool.
And this is going to be MEX, not to be confused with MX. And this is medium energy X-ray. So they're going to do a lot of work that is slightly lower energy X-rays than us. I'm not entirely sure what kind of science they'll be doing, but I'm looking forward to finding out. Now we're looking into, ready, another acronym. This is XAS. So you have to have a sort of degree in 3-letter acronyms to work at the synchrotron. This is X-ray absorption spectroscopy, and they do a lot of awesome environmental work in addition to a lot of other things. So one really cool example of the stuff that they're studying on this beamline is actually how to keep chocolate safe for our consumption. So apparently chocolate, so obviously chocolate's grown from cacao, or it's made from cacao beans. Cacao beans that are grown in South America have 10 times the amount of a toxic element called cadmium absorbed into them as they're growing when compared to chocolate being grown in West Africa. And so this is obviously really unfortunate for South American cacao farmers because they are going to miss out on a large market because they're no longer able to sell that chocolate because it's got too much of this toxic element in it. And what they're doing on XAS is they can actually look at the chemical nature of that toxic cadmium, and they can identify where it's actually sitting inside the cacao beans and how it's moving through those beans. And from that, they can help develop ways of processing the beans so that that cadmium is not carried through into the final product. So that means that those farmers working in those cadmium-rich soils can still make a safe product that they can sell and fall within the requirements for safety. So that's sort of an example of one of the cool things that XAS is doing. They also look at bushfire damage of Australian soil as well. So a lot of really important and interesting work coming out of that beamline. This is where Biofax is. Well, this isn't where Biofax is going to go, but this is where they've put the sign for it. I don't know why.
Look, they're just preparing or moving it temporarily.
Yes. So this is powder diffraction. This is a beamline that my D&D party, who are currently watching, will be very familiar with because a lot of them are geologists. And powder diffraction is a technique that geologists tend to use a lot to look at how different minerals behave. Something really cool that they're doing on powder diffraction is actually looking at analogues of Martian soil. So they're basically trying to figure out whether our Earth-made Martian soil is up to scratch compared to actual Martian minerals. So they have samples of Martian asteroids. I don't know if that's the correct term, meteorites. The geologists in the audience are going to be face palming. And they're comparing the makeup of those meteorites with what we on Earth have developed as a sort of faux Martian soil. And that's basically so that when we get to Mars, we have more of an understanding of how to use the resources that are already there to build things or to extract materials that we might need if we're setting up a colony there. So once again, if you pick a topic that you're interested in, dinosaurs, space, health, chocolate, anti-cancer treatments, whatever, we've got something at the synchrotron for you.
Yeah, right. Oh, I can see something else that's just about to come up that is also different once again. Tom, how are we going? Are you okay there? No?
Yeah, no, there's a question.
Okay. Oh, there's a question. Okay, I'm sorry. I missed a question. So Greg asked, how do they get these different energy levels on the different lines given all the source electrons are presumably at the same speed or energy?
Yes, a very good question. So the electrons are all at the same energy, and as they are whizzing around those corners, they are producing light or synchrotron radiation at a whole host of different energies. So everything from IR all the way up to our really high energy X-rays. And what we do is we actually use different optical systems to filter out the energies that we don't need and collect the ones that we do. So on the MX beamlines here, we have something called a monochromator. So mono, one, chromator, color mater, one color. So it's selecting one energy. We basically do this by having two silicon crystals that are spaced a certain amount apart. And the distance that they are apart allows us to tune and select for a certain energy of synchrotron radiation, because that radiation is going to come in, bounce off one crystal, bounce off the second, and exit. And if it's the wrong energy or the wrong wavelength, it's the same thing, it won't be able to make that full transition through the monochromator. And so we can actually mechanically change the distance and then therefore tune what energy we want to get out the other side. And then there's a whole series of mirrors and focusing.
Oh no. I think we've lost Eleanor, which is very, very unfortunate. Oh, hang on. Hi, Eleanor. Are you back?
Hello. Where did I get up to? I was so busy talking about monochromators, I disappeared.
That is probably the part that you got up to.
Did you see my hands?
We saw the hands. We saw the hands.
That's all that matters. We can select energy by moving our hands. No.
Oh gosh. We might actually move on to the next part of the video as I am tracking behind. We're having too much fun talking about all the different things that we've been coming across. There's so much going on. So okay, we're going quickly through this section, which I presume is another lab?
Yeah, so this is actually MX. So this is MX2. This is the beamline I work on as a beamline scientist.
So this is where you are right now?
This is next door to where I am right now. But yes, essentially. And this is the inside of our beamline. So this is the one I know the most about because I've used it as a researcher, and as a beamline scientist, our job is to maintain this equipment. So we don't have much to do with the accelerator, but this is our realm. So here in MX, we have robots, we have X-rays, we have everything you could possibly want and more. If you're interested in having, in the interest of time, it's totally up to you, Jirana, but if you want to sort of look at the different parts of the hutch, I'm happy to talk you through. But this is essentially how we set up experiments to identify three-dimensional structures of protein molecules. So that thing that was just in my hands there is one of our sample holders. We work with samples that are about the size of a width of a human hair, so in the order of 100 microns, or often quite a bit smaller, which is always challenging. We put the sample in front of where the X-ray comes out, so this little hole in that mirror in the center there. I'm not sure if you can see where that is. That's where the X-ray actually comes out. It hits our sample, and then the X-ray diffracts, so it scatters, a fancy type of scattering, and it hits this detector. So this is a detector that was actually funded by the Australian Cancer Research Foundation, because we do a lot of cancer research on the MX beamlines. Those scattered or diffracted X-rays are then analysed, and we can build a three-dimensional structure of the molecule that caused the scattering, the diffraction in the first place. Scientists in the audience will be frustrated that I'm conflating scattering and diffraction. They are different processes, and I'm happy to talk someone's ear off about diffraction any day of the week if you grab me anytime. I can show you what one of the three-dimensional models actually looks like if you're interested.
Yeah, I think that'd be really great to see.
It's all well and good to say, we can look at what a protein looks like. All right, well, what does that actually mean, and why does that matter? So this here is a 3D printed model of a viral protein. This one's actually from COVID-19. You can see that it's it's quite bendy, which is true to life. Proteins are very, very small, obviously. In order to get this structure, you have to crystallize the protein and then put it in front of our MX beamline. But the reason that scientists go to all this effort is because by having this available to them, by having this information, they can make more informed decisions about how to create drugs that interact with these molecules. So the analogy I like is that if you imagine trying to pick a lock, there's kind of two scenarios here. So you're picking a lock completely blind. You've got your lock pick and you're jiggling around. You're trying to design a key that's going to fit in that lock. Or if you're able to actually visualize the inside of that padlock, you can very rationally design a key that's going to fit in and perform the action of unlocking it. And that's kind of the key that scientists are looking for when they're designing drug molecules. They want it to physically interact with the biological molecule that it's targeting. And by having the three-dimensional shape of the biological molecule, they can make better decisions about what kind of chemistry they're going to do to interact with that system. So whether that's developing antivirals or anti-cancer treatments, or just looking at weird quirks like my research was, looking at how these sorts of molecules evolve in nature. That's sort of the end goal of this beamline. So we've got the whole accelerator, the whole synchrotron, and then the end result for us, at least, is to get this.
So is that what you see in this machine that we're looking right now, or what is this we're at?
So this is the robot. This is our robot who loads samples. So as I said at the start, I mainly use this beamline remotely at 3 a.m. in an office in Canberra. And the way I was able to do that is by driving this robot in order to mount samples that we'd sent ahead of time. And this has been obviously really fantastic in the last 12 months because it means we haven't had to have people on site in order to do research. This is me pulling the big heavy door shut. Obviously, safety at all times. The X-rays are kept separate from the people. So that robot means that we can have researchers in Singapore, in New Zealand, anywhere in the world, collecting data on our equipment at any time of the day or night. And they can sort of operate everything completely remotely. I think we're the only beamline that's sort of got that full capacity at the moment. Yeah.
So this is you setting up the sample now to run, is that right?
Yeah, so that's just sort of showing what some of the interfaces look like. It's more just to show off how many windows we can have open on a screen at once. Some of these will be things that the users who come in, the researchers who come in to do the science will see. And some of them are tools that beamline scientists have access to, for example, select the correct energy by driving motors in that monochromator, adjusting the mirrors to focus the X-rays as required. So this is where I'm currently sitting, in that window. Hello, past me. This is our cage robot. I'm showing you cage robot because he's about to be dismantled, which is very sad. But he's being dismantled because a new MX beamline is being built, MX3, which is going to be really just a completely new experience because we'll be able to do a lot more interesting science, looking at much, much smaller samples, doing really high throughput, so looking at lots and lots of different samples in a short space of time. And that beamline is going to be built basically right through here. And we are going to have to move all of our stuff to make way for it. But we're excited and not at all resentful of that.
I guess it means you'll be able to do more work once it's up and running. So yeah. I guess pro amongst the cons, yeah?
Exactly. Yeah.
Now, we have got a few more questions from the audience. I am aware of time, so I'll just take a few more questions because they are a little bit interesting questions as well. Yeah. So one question that has come through from Look at the Panda, great username. They want to know, how do you get the sample on such a small sample holder?
Oh, that is a good question. So I've got a sample holder here. I don't know if you can quite see. Squint a little bit. I'll hold it with my hand so you can see it. It is very small, and the way you get the sample on it is you have a scone and steady your hands, and then you sit at a microscope and you fish your tiny little delicate sample out of a microscope, out of a well under your microscope. So this is all done by hand at the moment because humans are better at doing this than robots are for now. And goodness me, when robots are good enough to do this, then people will never ever want to scoop up another crystal ever again, because it is a very, very delicate job. So you get very surgeon precision, steady hands, and you pick them up, and we typically will then snap freeze them in liquid nitrogen, so negative 180 degrees Celsius, and that protects the crystal from the radiation of the X-rays, so that you can shoot at the crystal for long enough to collect the information that you need without the crystal completely cooking. Yeah, and they usually get shipped to us in a big sort of temperature sense, like a big thermos, to keep them at negative 100, 180 degrees. But yeah, it's a good question.
And another question is, that sounds like really, really like it's mind-boggling how small things have to be to do these beamline tests. But it also means that, like, I guess you don't need a big sample to be doing this stuff, which is a good pro when working with things that might be very expensive. Another question we have is from Richard. How tight can they tune the wavelength?
How tight can they tune the wavelength? Sounds like Richard wants to do some experiments. And he's absolutely welcome to come on past. We can get our wavelength to, so if we're setting to like 13 kilo electron volts, it'll be 13.000 readback. So what's that? 13.000 kilo electron volts. So to within an electron volt on MX. On MX3, it'll probably be even better because that energy selection tool, the monochromator, will be even more precise as they sort of are using newer and newer technology. But yeah, the wavelength can be tuned very, very precisely, which is really important for probing small differences between different elements. So some elements are going to look very similar unless you're sitting right at the very edge of where they're going to interact with your light. So you want a very specific type of light to interact with a very specific type of chemical element. Yeah.
Oh, very, very interesting. Now, I am aware that we are running a little bit over time, but I'm aware that I've also got a whole heap of questions that have come through. There are a lot of excited, keen bean individuals that want to hear so much about you and the synchrotron. Are you okay to stay on for a few more minutes and answer a few more questions?
You will struggle to get me to stop talking about the synchrotron, Jirana.
Well, unfortunately, we will have to sleep at some point tonight, but I will take a few more questions just so that we can answer a few more and see what the public want to hear. So, first question on my list is, so each sample is just used once? It kind of gets destroyed, or what happens?
So it depends on the beamline. For us on MX, typically the samples are one-time use, but that's okay because people typically will grow a number of crystals of the same type. So they're sort of one-time use things. On different beamlines, they have less destructive techniques. So on the XFM beamline, so X-ray fluorescence microscopy, they've actually recently had an Arthur Streeton painting in front of their beam. So obviously that had to be signed off as, I think, am I still on? Yeah, I'm still on. That had to be signed off as being completely non-destructive because it was a piece of very famous artwork that they were then doing an analysis on the types of pigments and the different chemical elements in the paints that were used. They also do a lot of sort of anthropological and cultural analysis of different indigenous artifacts. So all of this has to obviously be dealt with really, really carefully, and their technique is non-destructive. So they can look at those samples without any harm taking place to the painting or the artifact that they're looking at. So yeah, it will vary beamline to beamline, technique to technique. On MX, once you've shot a crystal, it's probably not good for anything else anymore.
Oh, well, we'll have to keep that in mind when we next run our experiment team, which ones we can and can't reuse and recycle our samples on. But it's nice to know that we're able to, at least with some things. So my next question for you is, what is your favourite, most surprising study or result that's come out of the synchrotron that you know about?
That's a really good one. There's so much. I think one of the really interesting ones recently, and it will probably appeal, I know it'll appeal to at least one or two audience members. My parents and my aunt and uncle are watching, so hi. They have used the medical imaging beamline to develop ways of building prosthetic tusks for rhinoceri. This involved actually getting the skull of a rhinoceros and putting it in a big washing basket. That was their sample holder, a plastic washing basket from Target, putting it in front of the beam so that they could get a really highly detailed three-dimensional image of the inside of a rhinoceros skull so that they could better design prosthetics to fit to rhinoceroses who had been victims of poaching. So one of the sort of really tragic, horrible things about poaching is when poachers will remove the tusk of a rhinoceros, but the rhinoceros will still be alive. And obviously without their tusk, that's like us not having hands, that it's their key tool for interacting with the world. So by looking into how their skull actually works and how the tusk sits in their skull, using the medical imaging beamline, they could look into how better to design prosthetic tusks to put on those rhinos in the wild so that they can then go back to having a slightly more normal life. So that's a really, really cool example of one of the beamlines being used for something that probably wouldn't sort of occur to you as being something looked at in Melbourne, when it's affecting, lovely creatures on the other side of the world.
Yeah, I never realized it was working on something such like that. All I thought it was the synchrotron was working on was chemistry things. A very technical term, I know. But
that's what we call them here, chemistry things.
Yeah, just like small liquids.
Martian dust, rhinoceros skulls for prosthetics. They've put entire trees in front of the medical imaging beamline so that they could map how the motion of water through the trunks of trees. So obviously a lot of interesting things there. XFM, they were looking at the absorption of gold into gum trees. So gum trees can accumulate gold into their leaves because they're drawing it up through the soil. So they can identify that gold in the leaves of eucalyptus trees, and that then points to where there might be deposits of gold.
Wait, are you going to say that we're going to start mining gum trees for gold?
I hope we don't get too much into mining gum trees, but certainly as an indicator of where there might be different metals buried underground, the plant life can. It's been shown, thanks to studies on XFM, the plant life can accumulate that metal, and then you can see it in the spectra and the microscopy of the leaves of those plants.
Huh. Well, I think this was a great question to end on, because that is a lot of information that I now need to go Google. And I can probably see that some of our YouTube followers might start up their own entrepreneurial businesses. No ideas here. So Eleanor, thank you so much for joining us tonight. It's been really great to get to know yourself and what goes on behind the scenes at the Australian Synchrotron and all of this wonderful, wonderful abundance of information that you hold inside your head. Now, if people want to know more about the synchrotron or about yourself, where do they go?
Where do they go? Head to our website. So if you go to the ANSTO website, there's a little drop down that will put you in touch with the Australian Synchrotron. You can always contact the user office with questions. Just say Eleanor from MX sent you, and they'll forward it on to me. Otherwise, tweet ANSTO and the Australian Synchrotron. And yeah, we're always happy to get in touch with people. I think we're having an open day at the end of this year. So it's usually in October. So if you are in and around Melbourne, we would absolutely love to have you on site physically so you can get more of a sense of the place. And you'll already have some facts that you can drop in as you're walking around. But the open days, from what I've heard, are fantastic and people get a lot out of them. So please come past in person too, because we've missed having people on site and we really want to, get people back through the doors and having a look at all the amazing work that's being done using this equipment here. So, yeah.
And by then you'll have more beamlines, right? So we'll be able to see even more things by then. Yeah.
Yes, you'll see basically double the amount of stuff I just spoke about.
Oh gosh.
Yeah.
Well, on that note, thank you so much, Eleanor. It has been a pleasure to have you on board. To everyone across the internet, we hope you've enjoyed this tour of the synchrotron. If you enjoyed it, don't forget to head to our website to find out more about our next tour happening on Friday, where we'll be visiting a forensic chemistry lab with Dr. William G. Or if you're around tomorrow night, there's actually a trivia session going on, and it's not too late to subscribe if that is something that you're interested in. All of those details can be found on our website at pintofscience.com.au, and you'll be able to follow those links through. Now, we are of course a charity organisation, so if you'd like to see us keep on going, please donate if you can. Details can be found in the description of this YouTube video. And if that's not something that is your style, we do have some pretty cool merch that I would recommend highly. There's t-shirts, there's pint glasses, there's pins, all at different price ranges. So hopefully something in there takes your fancy. That is also going to help us keep on going as Pint of Science, the amazing thing that I hope you believe we are, and that I believe we are. So don't forget to hit the subscribe button to catch the video recording of today's event. If you've missed anything, or follow us on Facebook, Twitter, Instagram, we're everywhere. If you want to stay updated on all the Pint of Science content coming across over the next fortnight. Thank you so much for joining us today, and thank you to all our volunteers behind the scenes who made this possible, and we'll see you all next time. Thank you so much. Bye.